In previous chapter, you learned how to solve the elliptic PDE by using the numerical method such as the center finite difference method, where the d square t over dx square can be equal to this formula, and your d square t over dy square can be equal to this formula. So we call this as spatial difference approximation because you take the derivative with respect to the dimension x and dimension y. So basically this is the space x and space y. In general, the finite difference that deal with the dimension x, y, z, or what we call the space x, y, z, is called the spatial difference approximation. By substitute this finite difference equation inside the original formula, you should be able to numerically modeling the elliptic PDE and you should be able to obtain this equation. And you can rearrange the Tij to be equal to this. In fact, your Tij is equal to the temperature at the coordinate x and y, and it can be arranged into this formula. On the other hand, for the parabolic PDE, you have the d square t over dx square as well. Therefore, we can use the center finite difference method to obtain the d square t over dx square to be this formula. And compared with this previous d square t over dx square formula, you find that you have additional L variable on the top, and you can see that the subscript j is missing in this formula as well. This is because in the previous case, you want to find the temperature at the dimension x and y, which can be written into Ti, j, where your I is equal to the index for the x dimension and your j is the index for y dimension. If you add additional term d square t over dz square into this equation, that means you are going to find the temperature at the dimension x, y, and z. So we should include the index for this z axis as well. Let the k equal to the index for z axis, and you should find that we write the space index ijk at the subscript here. In the parabolic PDE, we want to find the temperature with respect to your x dimension and time dimension. Therefore, you have the t bracket x comma t. So we can write it in the index format where you have the capital T indicate the temperature. So you put the I indicate the index for the dimension x at the subscript here, and your L to be the index for the time, and we put it at the top here. To find the dt over d time here, we can use the temporal difference approximation. We call it temporal difference approximation when we take the derivative with respect to the time, and we call it the spatial difference approximation when we take the derivative with respect to the space x, y, z. We use forward type of finite difference method to find the dt over d time, which is approximate to be TIL plus 1 minus with TIL divided with the delta t. When we substitute the d square t over dx square and dt over d time into this parabolic PDE, we should be able to obtain the numerical modeling for this equation. Besides the equation 1 here, we can also use the equation 2 to find the second derivative of the temperature with respect to the x, where you can see the L is changed to the L plus 1. We can also find the second derivative of the temperature with respect to the x here, approximate to 1 over 2 of the equation 1 plus equation 2 to obtain the third equation. If you use the equation 1 for the numerical modeling, we call this method as explicit scheme or explicit method. So if you use second equation or the third equation here, we call it as the implicit or the alternative implicit scheme. Quite frequently, the alternative implicit schemes is called the Crank-Nicholson method. In this study, you will learn how to use these three methods to solve the parabolic PDE.